Thank you for the invitation. It's a pleasure to be here. It's my first time at the Field Institute. Thank you all for coming. So yes, today I'll tell you about some joint work with Otis Chodos, Kyung-Soo Choi, and Felix Schulze on mean curvature flow, specifically in R3 in a bit. But let me start generally and set up my notation so everybody's on the same page. So my notation will be that we will have, say, a family of hypersurfaces in Rn, or rather Rn plus 1, n-dimensional hypersurfaces in Rn plus 1, and they will evolve by mean curvature flow over some time interval I in R. If each point moves in the direction of the mean curvature vector. So the velocity of each point is given by the mean curvature of that hypersurface at that point. And the key properties to keep in mind that will be useful so eventually, and for the most part of the talk, I'll be applying this with closed, meaning compact and no boundary, embedded hypersurfaces. And so let me assume closedness here without really losing much generality. So a key property that I really want is avoidance, meaning if I start this flow with two initial conditions that are disjoint, and I flow, and they remain disjoint. So I'll call that avoidance. So if M, let's say 1, 0, and M2, 0 are closed and disjoint, then the flows remain such. Okay, so two disjoint things initially remain disjoint. Another property that you can see as coming as a straightforward consequence of this is that these flows develop singularities in finite time. In fact, they must develop singularities in finite time. So for a closed initial condition, because why? The easiest flow to consider is perhaps the mean curvature flow of a sphere, and we know that you can check by reducing it to an ODE, it becomes finite in a certain amount of time. And so if you enclose your initial condition in a large sphere, then eventually you will have to become singular because the sphere will go in collapse to its center point. So this leads us to finite time singularities. For closed initial conditions. So that's some singularities, like the one from the sphere, are singularities that you see and you say, okay, my flow just became extinct at this point. So you don't really care. There's nothing really that happens past that singularity. But there are some other singularities that I'll draw where you don't really want to stop your flow there. What's really happening is you're developing like a neck pinch and you want to do some kind of surgery and proceed the flow. So we will want to flow past singularities. So we will need a weak notion of flows, and there are various ones for mean curvature flow. And today I'll just assume one such measure theoretic notion. And I'll just tell you, we'll pretend that it's a flow through hypersurfaces, but really it's a measure theoretic version of that. And keep track of the measures correctly. And the key properties that it has is that it has long time existence past singularities, so there's flow through singularities. And I'll draw a picture. And it has a pretty good compactness theory. Which we will need in a little bit. Okay. And the notion that this is, just for your reference, if you want to be looking it up later, I'll be talking about what are called unit regular, cyclic, meaning it's a cycle, integral brachyflows. But if these words don't mean anything to you, I'll try to be drawing my pictures in a way that the pictures communicate what is important and what is happening. Okay. So if you look at the flow this way, then what you have to do if you want to be studying the flow is, let's say for a sphere, is that you have to draw your initial sphere, and then at that later time instant, you have to draw a slightly smaller sphere, and a slightly smaller sphere, and a slightly smaller sphere. So you would have to draw a bunch of pictures together. It's a bit more convenient if you take all these pictures and you stack them all one on top of each other, where you treat your time parameter as a kind of z-axis. And that allows you to keep track of a single picture that includes everything, and that is called the space-time track of the flow. So let me draw it here. So if you have a mean curvature flow mt over some time interval t and I, this gives you a space-time track, which I will denote by script m, which is the set of all points. It's, well, I'm going to say it as the union over all t and I of this set cross the time parameter. Okay, so in particular, this sits in my ambient space Rn plus 1 cross R. Okay, so I'm introducing a new axis. Okay, let's draw this picture for a couple of scenarios. So example 1, actually we'll have a couple of different facets. Let's say your Rn plus 1 is here, and your new axis, your time axis, is here. And let's say your initial condition is just a sphere of radius 1. This looks white anyway. So if your initial condition here is the unit sphere in Rn plus 1, then you can keep track via the ODE of how these things evolve. And you can see that it actually forms a paraboloid if you stack them all on top of each other. Meaning that these are the various time instances that I'm drawing here. Okay, and you become singular at this finite time, at the origin, at a certain predictable time. So this is time equals to 0, and this is time equal to a predictable constant 1 over square root of 2n. You can fit this into a bigger family, not just the spheres, but you can look at lower dimensional spheres cross R factors. All such things we will call generalized cylinders. So here's your Rn plus 1. Here's your R axis. And now your initial condition is, again, down here. And the cross section is some lower dimensional sphere. So M0 is some SK cross an Rn minus K. And if you flow it, then these spheres contract, kind of like this one does. And what it gives you is the product of this with various R factors. So it would look a little bit like this. And then the various spheres are here. So here you can, again, guess what this time would be by, oh, here you develop a line of singularities. And you can guess that this is going to be at this predictable time. Sorry, yeah. I'm thinking of R3 later, but yeah, no, it's not a line. Yeah. Sorry. When it is a line, a lot more tools are available to us. It's just one of the reasons that the R3 case is more manageable. Okay, so here's just to get the sense of this kind of picture. If you haven't been seeing many of them before, let's draw something else. Let's say you take your Rn plus 1 here. So let's take an R3. And let's take this kind of dumbbell shape around here where let's make one lobe a bit bigger than the other. Then what happens is, okay, here's the lobe. What happens is that this neck here under the flow contracts first. It develops a singularity. And then the smooth equation would then fail, okay? Which is why we need the weak equation. What the weak equation will do, it will allow us to flow past this singularity. It will basically, there will be a surgery. It will decompose this dumbbell shape into two spheres, which then this will contract first and then this will contract later. So how do you draw this shape all together? If this is the initial condition here, then this would look perhaps something like this, where at first you're doing what I was saying, is you're developing like this. Then eventually you develop a singularity. So you get one singular point. Then you keep flowing. You develop the second singularity. And then this component dies, and then you develop this singularity. Okay? So it's a convenient way to encode the whole process into one picture. So I should mention here that hopefully this picture helps make a convincing case as to why one might want to flow, because this shows you kind of like how the kind of surgery process would go. If you were trying to, instead of studying weak mean curvature flows, studying mean curvature flows with surgery. So there's that's a whole different orthogonal direction to what I'll be talking about. But Huskins and Estradi have done work. Brendel Huskin, Bob with Bruce Kleiner, and so on. So that's one direction one can go in. To be able to do the surgeries or to even understand these pictures, we'll have to go into analyzing our singularities. There's various ways to analyze singularities in analysis. The one that will be sufficient for this talk is zooming in and just taking a blow-up limit, okay, at a fixed point. So let's make this precise in the setting of these pictures. So if you have some space-time track M, I'll want to be able to dilate by a factor of lambda, and I'll send lambda to infinity. So what notation am I going to use for that? I'm going to say I'm going to parabolically dilate by lambda my space-time track M, which means I'll take all points in M, x comma t, and then I'll scale x by lambda and t by lambda squared, because that's what scaling looks like if you want to preserve the parabolic structure of the equation this is a solution to. All right, so then what you do is, here I'll be hand wavy, but then the idea is you fix your preferred point when you want to take a blow up. So let's say you fix some x0, which is going to form little x0 comma t0 on your space-time track. You choose some sequence of positive lambda i's going to infinity. You take this picture, you bring it to the origin, and then you parabolically dilate. Okay? So then you define mi tilde to be the parabolic dilation under lambda I of m translated backwards so that x0 goes to the origin. Okay? This is a space-time track for a mean curvature flow. For example, here, you'd be bringing this back down here, and you would keep rescaling. And then, using the compactness theory that this weak theory allows you to use, you can hopefully pass to a subsequent, you can pass to a subsequential limit in a suitable topology and get an object, which is a space-time track of a weak mean curvature flow, m tilde, which I will call a tangent flow to the original space-time track m at the point x0. So what does that look like there? So back to the examples. So in example A, what happens is when you do this, because this flow is self-similar, it just moves by shrinking at the right rate. What happens is if you move this down here, you take a tangent flow, you get precisely a copy of this thing. Oh, let's agree to the notation that whenever I do this and I take this limit, then I throw out whatever is for positive times. I'm only studying what is happening for negative times. There are some subtleties there. So here, what happens is we move to the singular point here, and then notice that when I'm rescaling, this thing goes farther and farther out to infinity, right? So I'm getting a complete paraboloid. So here, I'm getting a complete paraboloid m tilde, which is of the form union over all negative t's of, let's see, the square root of negative 2 square root of negative t times Sn square root of 2n cross time t. So this is the sphere being rescaled at a suitable rate and then being stacked all on top of each other. The other picture with a cylinder likewise becomes, oh, sorry, this is the time axis. Likewise, your singularities go up here. Your initial condition gets sent down to negative infinity. And this becomes the union over negative times of square root of negative t, sk square root of 2k cross Rn minus k cross t. This is what happens when you blow up at any of the orange points, okay? So this is if x0 is any of the orange points. Right? But as a thought experiment, you could conceivably pick an x0 that is not a singular point and blow up there, just to get some intuition as to what's happening. So in that case, if you pick some x0 that is not a singular point, and you do a parabolic dilation, you send limits to infinity, what happens is you can get a fixed hyperplane that stays invariant as you go down to time negative infinity. That hyperplane is a tangent plane at that point. So for any other x0, let's say with positive time component, you get this where there will be a tangent plane, let's say this one, which will be tx0 m t0 if x0 is of the form x, little x0 comma t0, and this will be, you'll just have these statically down to time negative infinity. This is in general dimension. This is in Rn plus 1. So this is a hyperplane in Rn plus 1 in each slice. And then it's the same thing down for each factor.
I'm sorry.
No. Yeah. This is what happens when you don't have a singularity.
Yeah, no, I understand that. But you said in the previous picture, we would always get one of these two pictures unless.
Of the ones that I drew.
Yeah.
Yeah.
Oh,
There's
okay.
no classification of singularities. Yeah. Yeah, that's the main difficulty.
I
Yes.
see. And in lower dimensions, there is a classification of similarities? Or?
What is a low dimension for you?
Or-
In two, yes, we know what happens because that's curve shortening flow. In three, for embedded case, there are no singularities. Otherwise, you have these average Langer curves. For 3 dimensions, there is no classification of singularities. Yeah. Right. So then here, the picture you get is just this static guy, T x0, mt0 cross T for all negative times. Again, because I'm throwing out what happens afterward. All right. What happens in the second picture that I had drawn? In the second picture, if I blow up at this point or at that point, I get this. If I blow up at this point, I get this with K1 and 3. Sorry, K1 and 1. So, sorry, what am I? K1 and 2. I'm in R3, which is n plus 1. And if I blow up anywhere else, I get the tangent planes. So in example B, I'll just say a combination of the above. Okay. Another small but important note is that here, I generally don't know that this tangent flow is unique. Okay, it can depend on the lambda I, except in certain situations, which include the situations that I've drawn, unfortunately. Okay. To get a better understanding of what happens for a general mean curvature flow, you need to just refine. Yes? It's unique if you know in the following situations. We know it when your tangent flow is a hyperplane. That's Brachy's regularity theorem. You know it when your tangent flow is a self-similarly shrinking generalized cylinder. When one, then they're all hyperplanes and they're the same one. Then when you have one tangent flow that is this, then they're all of this form and with the same axis. They don't rotate. That's a theorem of Colling and Minicozzi. And well, the first one being that without the rotation part is called an Illman-Minicozzi, and then with the axis part is called in Minicozzi. If you have a tangent flow that has a compact cross section, so slightly more general than this, again uniqueness by work of Felix Schulze, and beyond, and then also asymptotically conical ones. So, but we don't know it for all of them. It's generally quite delicate.
For all those common stuff, it's unique, but different people.
Right.
Conical.
And compact. Yes. All right. So how do you justify these the self-similarity, meaning you seem to have one object here that just seems to be shrinking. That's what seems to be happening in tangent flows. Here, okay, the plane doesn't seem to be shrinking, but really if you take an Rn in Rn plus 1 and you scale it down, you still have an Rn. Okay, so this is fake shrinking. Here, you're legitimately shrinking. Here, you're legitimately shrinking, right? So how do you set up this theory? So here you need Huskins monotonicity. So the main quantity here is for, let's say, hypersurfaces sigma in Rn plus 1. Let's define this F quantity to be some multiplicative constant C of n times a Gaussian integral over sigma. For the purpose of this talk, it doesn't matter what the Gaussian is. And you choose this so that if you plug in a plane through the origin, you get one. Okay. With sigma n such that f of a plane through the origin, I'll just denote it with Rn is equal to 1. Okay, now once you have this, then you can define the Huskin density for a flow, including weak flows. For a weak mean curvature flow, possibly you define and a preferred point. Okay, let's be precise. For a weak mean curvature flow, for times some interval from some amount of time, maybe 0 up to infinity, you can always think of the flow as going out to infinity in the sense that it might possibly die after it has become extinct. And for a preferred point where we will be taking our blowups, script x0, which is little x0 t0, you define theta of the space-time track at this point at scale r to be the f quantity applied to, you can think of it in two ways. Take x0, move it to the origin, parabolically dilate by 1 over r, and then look at the t equals -1 slice. Or equivalently, it's 1 over r of m at time t0 minus r squared minus x0. They're both the same thing when you unwrap the definitions. Notice that as you're sending r to 0, then you're going closer to the singular point, right? You're measuring what happens closer to the singularity. And this is well defined as long as this makes sense. So you can take it for r's between 0 and whenever this makes sense. So square root of t0 minus a, the starting time. So yeah. So then what do we know about this? We know a couple of things. First of all, it's non-decreasing. So for r1 less than r2, we have that theta m at x0 r1 is less than or equal to theta of m x0 at r2 with equality precisely attained by self-similarly shrinking flows. So with equality, if and only if m is self-similarly shrinking about x0. In other words, if this guy does not change as I'm changing r. So in particular, what this means is that for times less than t0, what is going on is your space-time track is of the following form. Square root of, let's say correctly, t0 minus t times a fixed guy that is what you will be seeing as your fixed object here, cross your time factor. And this we will be calling a self-similar shrinker, meaning if you were to start a mean curvature flow with that, it would just be shrinking with the corresponding rate. Now, so here, this looks easiest to interpret in the smooth setting, but it also applies to this weak setting of mean curvature flows that I'll be getting into. All right. That's one thing. Incidentally, if indeed that is the case, that my flow is self-similarly shrinking, and because these two guys are constant, then the theta at these, in all these scales, is equal to the f of that guy's sigma. Okay? So let me write it in a couple of different ways. And that's one thing. Moreover, because of the monotonicity, we can actually define the infinitesimal density at the point script x0 to be the limit as r goes to 0. This is in general by monotonicity. Let me call it number 2. You can define this. And finally, you can put these two things together to help you understand what these tangent flows look like. So let's go to the tangent flow setting. Mu tilde of m at x0. If you go to the tangent flow setting, then m tilde, what happens in this monotonicity formula is you're taking r and rescaling it to unit distance. And so this monotonicity tells you, after you take limits, that the tangent flow spacetime track has this equal to a constant, the constant being the limit at time equals 0, because you have plateaued as you're rescaling your picture. So in particular, for tangent flows m tilde of m at x0, we have that this quantity at the origin, which is where I've sent x0 to, is constant. And which constant is it? Well, it's the constant density at this point, but also because it's a constant, there's an underlying sigma associated with it, which is the self-similar shrinker. So for example, the sphere in the top 2 singular points, or the cylinder in that middle neck region, or Rn in the other regular points. So this will be f of sigma for possibly a weak, meaning possibly singular, self-shrinker sigma. So one of the extra headaches in going from R4 to higher is that you really have to start worrying about possibly singular solution self-shrinker sigma. But in R3, we will see that we will be able to reduce to the smooth setting for these sigmas, which is a major improvement. This sigma is that sigma. Okay. By the way, just to clarify, to write it again here, m tilde will be the union for negative times of square root negative t of this fixed sigma cross t. Okay. All right. So there's 2 things that can happen, and this is a difficult theorem. It's called Brache's regularity theorem.
As for the entropy F should be depend on the choice of x there.
For sure, yeah. The choice of x0, right?
Yeah.
Yeah. So let me tell you here. So because this will depend on the choice of x0, sigma. So in part, 2 possibilities, well, many possibilities. The possibilities of this density at x0 are that it equals 1, and the 1 comes from exactly when you blow up and you see a static plane. So +1 if the blow up was at a so-called regular point, where you actually have a legitimately smooth flow around there. Or otherwise, it will have a gap. It'll be at least 1 plus a fixed delta n, some positive number, for blowups at singular points. So in the picture that I drew with the 2 peaks, if you blow up at a regular point, you get 1. If you blow up at the tips, you get your second lowest density. And if you blow up at the neck pinch, you get your third lowest density. Okay. All right. Oh, again, this is a theorem. This is not like an easy fact, right? This is called Brache's regularity theorem. It's a fixed gap away from one. So, sorry, where should I be looking? Who asked? Yeah, sorry. So all the densities for singular points, they can't get arbitrarily close to one. You have to have a fixed gap from how close they get to one, which depends only on the dimension. And we don't know. Yeah. And we don't actually, it's a nice problem to try to figure out the sharp version of this, and we still don't know.
And do you know something about sort of the different levels, the spectrum or whatever?
Yes, we know some stuff, but the one that we know best is R3, where you have the plane, you have the sphere, the cylinder, and then everything else. And that is already a difficult theorem.
And is there a gap above the cylinder?
There is, yes. The corresponding thing is not known for R4 and higher.
But it's not.
Kind of like levels, F? That I don't know. Yeah. Bob, do you know? Yeah. Possible. I mean, if you draw the analogy with minimizing surfaces, maybe, but yeah, I don't know. Okay, so what are the various singular point blowups that we could have? So various sigma are possible. So you could have.
That's like for higher end, it could be achieved by Y shape.
What could be achieved by Y shapes?
It's the
Well, in Y shape specifically, no, because I'm assuming cyclic flows, but yeah. We do know that the least one is attained by the sphere, but that's all we know.
This one sphere is certain.
Yes.
For every dimension.
Yes. Okay, so what sigmas do we know? We know that sigma can be a plane, meaning hyperplane. The points x0 that satisfy that, I'll call regular points. In all other cases, I'll call that x0 a singular point. So it could be, sigma could be a generalized cylinder with multiplicity 1. Here also with multiplicity 1. And sigma could be lots of other things, even in R3. There's a whole industry of creating self-similar shrinkers. So maybe the easiest ones to draw are the Angan and Torus, which self-similarly shrinks about the origin if you rig the principal curvatures just right. And there's also a genus 1 asymptotically conical self-shrinker. I think Chop constructed this, and this self-similarly shrinks and blows down to a cone. Okay. All right. So, oh yeah, and these are the singular points. And in fact, we will want a slightly more refined classification of singular points into roughly these 3 classes. Let me write this down. So classify points of the space-time track after the initial condition. Into the following classes. There are the regular points, which I denote by reg m. These are essentially the points where my flow is smooth near them. Equivalently, these are the points by this theorem that have density equal to 1. Then you have your singular points, which are the remaining points. And among the singular points, I'm going to decouple these from all the others. I'll call these, okay, this is a non-standard. I'll call these my good singular points, and I'll call these my bad singular points. And I'll explain to you why I'm using this non-standard notation. So I'll say sing good of M to be the singular points with blow up, with tangent flow, a shrinking generalized cylinder. With multiplicity 1, as always. And my bad singular points will be all the rest.
And what cylinders includes?
Yes, here, yes, yeah. Sphere. So in R3, spheres are cylinders, and in higher dimensions, any k from 1 to n minus 1. Or to n, sorry. Right, okay. So let's now go down to R3 from this point forward. It turns out these what I call good singular points are, first of all, points that Gerhard Husken conjectured will be the only ones to appear for generic initial conditions, meaning these ones we don't expect to appear for random initial conditions. So let me state that as a conjecture. For generic, for example, you can think of bare generic, some open, dense, or countable intersection of those. Initial condition M0 in R3, closed, embedded, and so on. The mean curvature flow, the weak mean curvature flow M out of M0 only has these guys, aka has this one empty. Okay. Now, this leads us to think of these points as being the points that we want to be generic, the generic singular points. Now, if you go into the literature, you will see that by definition, this is called the generic part of the singular set, and this is called the non-generic part of the singular set. But that was an aspirational definition, right? We do know now for R3 this is the case, but don't let the literature confuse you.
So this means
Yes, so yeah, now true. And I'll tell you of a proof today. Yes, yeah. With Kyung-Soo and Otis and Felix, and it also requires the work of Baumler and Kleiner on the multiplicity 1 conjecture to deal with these kinds of things that are tricky. All right, so intrinsically we like these points, which is why I call them good, but we actually like them for more reasons than that. We like them because, for example, if you combine the work of Bob and Kyung-Soo Choi or Hershkovitz with some work of Josh Daniels Holgate, you can prove that you can actually, in R3 at least, legitimately view these points where you do surgeries. It's exactly the picture that I was telling you about in the beginning. So these we like because of that reason, and also because these are the points where even though you develop a singularity, your solution is kind of well posed. It exists uniquely. There's no dichotomy of behaviors after the singularity. These points we do not like, the bad ones, because all sorts of nasty things happen. We don't know, and very often there's no uniqueness of the solutions past them, and we just don't know how to interpret them geometrically as well as these guys. Okay, so it's great if this is true, which it is now, because it means that you can just wiggle these away and just understand to some extent what your mean curvature flow does. So let me tell you what the strategy is.
Generic involved markings.
Yes, so in the proof, what it means is that it's an open and dense subset of the space of hypersurfaces. For example, you can look at the space of graphs over this and look at an open dense space of C infinity functions to graph over this.
How important is that the ambient space is Euclidean space?
As opposed to a manifold, you mean?
For manifold, maybe, right?
If it's in 3 dimensions, it's not important. In higher dimensions, we don't know.
But in high dimensions, who knows? Or C, or M.
We don't know whether this is true. Yeah. All right. So here's the approach. So let's say you have your initial condition. What you do is you don't just look at that initial condition. I think this idea goes back to Illman and others. You don't just look at this initial condition, but you look at a family of initial conditions that includes this one. So you call this M0 of the 0 family. And in general, you take a monotone perturbation, meaning one with like a graph of a positive function or something. And you surround it on both sides with initial conditions MS0 for some small parameter s. Then you let everything flow. So you take this to flow and develop some singularities. You take the inner ones to flow, develop some singularities. And you keep track of all the space-time tracks script ms. Okay? Now, by avoidance, because these initial conditions are disjoint, these space-time tracks are also disjoint from each other. This is by the very first thing that I said, the avoidance principle. So if you arrange M0 S0 to be pairwise disjoint, then the MS's are also pairwise disjoint by the avoidance principle. And so we'll be trying, we are studying the various singular sets here. All right. Now, as I was saying, if these singular points were to occur, then from that moment onwards, the flow is very hard to understand. Basically, all bets are off. So we need to find a way to reduce the problem to one where we stop paying attention once at least one of these has occurred. So let's set this up correctly.
For ICS is
ICS, it's a small parameter from negative epsilon to epsilon or something. Yes. Oh, yeah, sorry. This one? Initial conditions, sorry, yeah. So here's our reduction. Let's define the first, what I call the first bad time. Formally, I define it as the inf of all the times t, where there is a point xt in the bad singular set. So really, it's the inf of bad times. Now, it's a theorem, hard theorem. So this combines the work of Brendel and Bernstein-Wang. So by a theorem, this was, as I'm writing it, follows from the work of Bernstein and Wang, but it really uses Simon Brendel's work. That this is equal to a min, that this is actually attained. That's why I'm calling it the first bad time. Okay. Of course, if the set is empty, I'm happy, right? If this set is empty, I'm happy. So in that case, I won't consider, or if you want to have a definition for it, you can set it to be plus infinity. So then I'm going to restrict my attention to not the whole bad singular set, but only the one that occurs at the first bad time. It could be one point, or it could be a bunch of concurrent points. It doesn't matter. Actually, no, let's do this. So then restrict your attention to sing bad superscript 1 M to be the set of all bad singular points at the bad time. Okay. So it will be some, subset of, let's say, this point, and then this point, and maybe this, and then this point and that point. Just schematically. Yes.
Make sure like and once without is especially for the bad singularities or for all singularities it can be achieved.
That it's for all singularities, that's an easy fact.
Uh,
It follows from the fact that the singular set is closed.
oh yeah.
But for these,
Oh,
it's hard.
okay.
Yeah. Lu Wang, sorry. Yeah. Yes. You mean here, right? Yeah, sorry. So how are we going to prove that generically we're okay? Our goal is to prove, oh, by the way, by definition, in fact, by the theorem of Bernstein-Wang, showing that the whole singular set is, there's no bad point, or it's empty, is equivalent to the first bad time being empty, right? So it suffices to show that there's no first bad time. Okay, which is a smaller set. So suffices to study this guy. And how are we going to prove that? What's the goal? The goal is to prove that all S1 bad, the union of all the bad singular sets over the S's, the initial condition, so the S is how far along the initial condition family you're going. S equals 0 is the original one, and positive S is on the outside, negative S is on the inside.
Okay.
Yes. Yeah. Like take a function and you graph over it, some small multiple epsilon. And so what we're going to show is that the union of these first bad singular points is discrete. In particular, because we're living in a compact set, it's finite, and so only finitely many S parameters are bad. Which implies the conjecture. Okay, if we prove this. This is the difficult part. All right. I think this picture is a bit more important. So how do you prove something like this? By contradiction. So go by contradiction.
Can you remind me about this statement of discrete again? Like,
What does discrete mean?
oh, no, just let's see the statement again.
I want the union of all these things. I don't think there's more colors, but yeah. The first singular points, their union to be a discrete set. Yeah. And do you see why that implies once that's discrete, then only a discrete number of S's have such a point. So all but the finite number of S's are okay. So let's suppose this were not the case. Then you would have some singular point. Let's say it was not discrete and there was some accumulation point somewhere. So you would have some accumulation point here. Let's call it X0, which belongs to the flow MS0. And there would be some nearby, arbitrarily close by, other points in that set in MSIs. Okay, so X0 is in Sing 1 bad ms0, and this is in sing 1 bad msi. Okay? And this is of scale little o of 1. What I'm going to want to do is I'm going to want to dilate this, take it at a fixed distance, and pass to limits. What this will give me is what am I doing here at this specific x0 is I'm taking a tangent flow at that x0. This is where the Baumler-Kleiner theorem comes in. Their multiplicity 1 theorem implies that tangent flows at points x0 in the first bad singular time, we don't know it for the subsequent ones, are the usual thing, shrinking flows, but with sigma being smooth, this we know from the work of Ilmanen, multiplicity 1, shrinker that is not a sphere or a cylinder. Plane, sphere, or cylinder. So this follows from their work, which means that if I take a tangent flow here by dilating this and passing to the limit, I know that this one will converge to a shrinking flow based at the origin.
You don't have any.
We don't know uniqueness except in the situations that I mentioned earlier. Yeah. So you have a shrinking flow that is centered now at the origin, which is where you take your parabolic dilations off of this, right? And you have, I don't know, some shrinking flow going backwards in time. And this will be some self m tilde of some sigma. Now you've also sent your other point at a distance 1. Let me put it here. And there's not enough dimensions, but remember there's the avoidance principle, which tells me my initial flows were disjoint or disjoint. So these two things that I blow up to will also be disjoint, but this one will be a flow that is contained on one side of this flow. So this point here became a point x tilde in some flow m prime. A priori, if you don't do things correctly, this is distance 1. If you don't do things correctly, that's all you can tell. Now, you have to do a clever stratification argument by densities, which I can't get into, but by a stratification argument, you can ensure that when you do that, you only do this and end up with points that are shrinking here and shrinking here, based off of two self-similar shrinkers. I can ensure that m prime is also m of some sigma prime blown up, plus some translation. So you have one self-shrinker whose track is contained in the track of another self-shrinker. There's a Frankel type theorem, which tells you that if you have two shrinkers whose tracks are disjoint, or well, they don't cross each other, disjoint or equal, or yeah, they don't cross each other, then they must be the same shrinker. So sigma prime and sigma are the same thing. Actually, yeah. So in my bad situation, I have a shrinker sigma, so that m tilde sigma and m tilde sigma plus some translation don't cross each other. In the pictures that I've drawn so far, by the way, this is viable, for example, by the sphere, because I can take another self-simulated shrinking sphere and put it here, right? It's also true for the cylinders, because I can, again, put it inside. And it's true for the plane. I can move the plane over to one side. The theorem is these are the only ones that satisfy this. Okay? If you can prove that it's the only ones that satisfy this, then you could not have blown up and gotten a shrinker that is not a plane, sphere, or cylinder. So let me just write that down.
Sorry, I still didn't figure out like why stratification applies in the translation right now.
Sorry, what?
Like how does stratification argument applies to?
Well, that will be a Q&A. That's very technical.
Roughly speaking.
Again, Q&A. I mean, that's very technical. Like, I don't have any. Let me finish the thing and then I'll.
Oh,
Yeah.
sorry.
So the theorem is, suppose you have a smooth shrinker, multiplicity 1, sigma in R3, and some point x prime in R3, which is not the origin, meaning this point that I'm translating to, and m sigma is disjoint, m sigma tilde is disjoint, or does not cross m sigma plus x prime. Then sigma is a plane spheral cylinder. And then we're done.
Det tänker på det sättet att det finns det här. Vad man väl kan beställa det. And what questions by Christos?
I can go over, yeah.
Roughly speaking, how stratification argument implies must be some translation.
No, I'm not saying it must be self-simulated shrinking. That's what it implies. Then the Frankel says that it's a translation of the same thing. So how do you imply this? You chop the bad singular sets, the first time of them, into bits where the density does not drop too much from scale 0 to some scale r. And if you arrange this drop to be little enough, then you get, it's like a quantitative differentiation argument. Then you get that all the points that you are seeing are approximately self-shrinkers. Yeah, and so you conclude that all these points, by taking limits or a contradiction argument, are legitimately self-shrinkers.
And like this argument here, Frankel property implies exactly same.
Yes. Basically, if you have a shrinker, the easiest way to say it is the following. Let's say you have a shrinker sigma and another shrinker, which is contained in one of the two components of the complement of sigma. Yeah, then they must be the same thing.
Frankel property in this context.
It comes from the Riemannian geometry Frankel property that if you have two, let's say, minimal hypersurfaces in positive Ricci curvature, and they must intersect. So it's the same thing where you're looking at the space of shrinkers, and you're saying that any two of them must intersect. That's all. Any positive one parameter family, yes. Yeah. I need the avoidance, right? If it's not a positive family, then it's going to cross itself. And
It was a little bit confused by the back of the argument where you said discrete can go to infinity in time, or
no, because remember the avoidance principle tells you can put a huge sphere around everything, and that will become extinct at some point, which means that everything became extinct beforehand. So you can ensure it's compact.
But it's definition, plus the minus.
No, but I'm starting at t equals 0, right?
Discrete is much more than we put down.
Yeah. Yeah.
Faster. Whoops.
very good.
Jesus. Yeah.
Okay.
Yeah.
So I'm still confusing. After Franco's property, we claim they're equal. Like, how do we claim exactly they should be disjoint? Like, how do we conclude this their statement?
This statement,
Yeah.
because of how I've rigged things. Remember that all my tracks in my original picture were disjoint, right? I moved my initial condition to one side. So any 2 points that I look at have disjoint tracks. So then when I do my blow up, I'll get limits that are, okay, there will be weakly disjoint, meaning this will be contained in the closure of the complement of this. That's what I mean by disjoint. They don't cross. That's what I mean. Like you don't have going into both components. Yeah.
And what we assume by contradiction is they are close, but arbitrarily close.
No, I'm assuming by contradiction that this here and that here are first bad singular points.
Yeah.
They were very close, so I'm blowing up. I'm dilating, which takes this and turns it into a tangent flow.
Yeah.
By my initial stratification, this also turns out to be a tangent flow. Well, it turns out to be self-similar. So then I have 2 shrinking flows on one side, one weakly on the other side of the other. By Frankel, it's the same shrinking flow on one side of itself. So by this theorem, that can only happen if the shrinker that these are based off is a plane, a sphere, or a cylinder.
Okay.
But that's not the case because that's where I was blowing up at all the other ones.
Okay, I see. But you are blowing up 2 singularities.
Yes.
At one.
That's what's delicate, yes.
But when you blow up, we are blowing up at exactly the point, singular point, right?
Well, I'm dilating at this singular point and I'm sending this to distance 1.
Yes.
Yeah. Which is why this becomes a tangent flow
Yeah.
immediately, and this one might not.
Yeah, this one might not. Yeah.
That's why I'm stratifying. I'm ensuring the density drop is uniformly small in small scales at both, which will turn this into a self-similar shrinker too. That's the tricky part.
This is by so-called constitutive.
Yes. Yeah.
Is the stratification argument similar to your work generic?
Yes, this paper, so there's a way to prove this conjecture with a lot more work by showing not this way, but that the genus drops after every bad singularity. But that's a lot longer. And we figured this approach out after our other work on the generic minimization for minimizing hypersurfaces, which is a bit different flavor. But yeah, it's been a zigzag between these 2 things.
Also, you had a version before bounded line itself?
Yeah. That version is basically contingent on their result. Yeah.
But after it came out, you had another paper.
Yeah, so that paper I was not involved with.
Oh.
Yeah. So there's 2 solutions. One is with genus drop, which is the paper that I was involved with. And the other one I wasn't, pre-Baumler-Kleiner, which were contingent on Baumler-Kleiner. So once Baumler-Kleiner proved multiplicity 1, then together they implied genericity. And then afterward, we found that there's a very short, I mean, this paper is, I don't know, like 10 pages long. So we found that there's a very direct way to go about it.
Using Baumler.
Both times, yes. Yeah, I don't know of a way to go around.
Where exactly the contradiction in the
That I'm blowing up at bad singular points, which means my tangent flows must not be plane spheres or cylinders. And I'm why? I'm proving by contradiction the discreteness of this set. So if it were not discrete, there would be a preferred one and some sequence going into it.
Yeah, I see. So why are you
To do the blow up, to take this. Yeah. Sorry. Yeah. This little O of 1 becomes an actual 1 there. Yeah.
Okay, that's again.